The discovery of a planet with a highly elliptical orbit around an ancient star could help us understand more about how planetary systems form and evolve over time. The new planet, HD 76920b, is 4 times the mass of Jupiter, and can be found some 587 light-years away in the southern constellation Volans, the flying fish. At its furthest, it orbits almost twice as far from its star as Earth does from the Sun. Details of the planet and its discovery are published today. So how does this fit into the planet formation narrative, and are planets like it common in the cosmos? Read more. A fleeting visit, an asteroid from another planetary system just shot past Earth. The solar system before the first exoplanet discovery. Our understanding of how planetary systems formed came from the only example we had at the time, our solar system. Close to the Sun orbit 4 rocky planets, Mercury, Venus, Earth and Mars. Further out are 4 giants, Jupiter, Saturn, Uranus and Neptune. Scattered in their midst we have debris, comets, asteroids and the dwarf planets. The 8 planets move in almost circular orbits, close to the same plane. The bulk of the debris also lies close to that plane, although on orbits that are somewhat more eccentric and inclined. How did this system form? The idea was that it coalesced from a disk of material surrounding the embryozoic Sun. The colder outer reaches were rich in ices, while the hotter inner regions contained just dust and gas. Over millions of years, the tiny particles of dust and ice collided with one another, slowly building ever larger objects. In the icy depths of space, the giant planets grew rapidly. In the hot, rocky interior, growth was slower. Eventually, the Sun blew away the gas and dust, leaving a relatively orderly system, roughly coplanar planets, moving on near circular orbits. The exo-planet era, the first exoplanets, discovered in the 1990s, shattered this simple model of planet formation. We quickly learned that they are far more diverse than we could have possibly imagined. Some systems feature giant planets, larger than Jupiter, orbiting incredibly close to their star. Others host eccentric, solitary worlds, with no companions to call their own. This wealth of data reveals one thing: planet formation and evolution is more complicated and diverse than we ever imagined. Core accretion vs dynamical instability. As a result of these discoveries, astronomers developed 2 competing models for planet formation. The first is core accretion, where planets form gradually, through collisions between grains of dust and ice. The theory has grown out of our old models of solar system formation. The competing theory is dynamical instability. Once again, the story begins with a disk of material around a youthful star. But that disk is more massive, and becomes unstable under its own self-gravity, causing clumps to grow. These clumps rapidly form planets, in thousands of years. Both models can explain some, but not all, of the newly discovered planets. Depending on the initial conditions around the star, it seems that both processes can occur. Each theory offers potential to explain eccentric worlds in somewhat different ways.